Hello. One of the more amazing stories in science is the discoveries that led to the true nature of light. Now you might ask, why is light so important to chemists? Well, utilizing light to probe matter by the method of optical spectroscopy led us to understand the very nature of matter and is a primary tool in modern labs to understand the electronic structure of matter. Now we're going to first look at the various properties of light and try to quantify the relationship between light and the energy that the light represents. So, let's get to it. Remember our friend Michael Faraday who discovered chemical ions? Well, he once again shows up in our chemistry story. In 1845, after a series of beautiful polarization experiments with light, he proposed that light could be a form of electric and magnetic fields, which led to another name that light would be called, electromagnetic radiation. In 1873, the great James Clerk Maxwell formulated a mathematical description of light, picturing the electromagnetic radiation as an oscillating wave with varying electric and magnetic fields at right angles to each other. And like all waves, we can describe the light waves as having a characteristic wavelength by measuring the distance between the peaks in the wave. The units of a wavelength would be length, meters and SI units, per one single wave cycle of light. And we could also describe the light by its frequency. If we stay at a certain spot and count the number of peaks that come by us in 1 second, the number of waves we count would be the frequency of the light. The unit for the frequency measurement is Hertz, Hz, quantifying the number of wave cycles of light that pass in a single second. These two measurements of light, wavelength and frequency, are important. If we multiply the wavelength of a light by the frequency of the light, we get a derived unit of length per second, which we know from physics is the same unit as speed. So frequency times wavelength is the speed of light, which in a vacuum is always a constant, with a value we already know and have used in previous lectures. So if we know either the frequency or wavelength, it's straightforward to calculate the other missing quantities using this formula, since we know the speed of light constant. In 1887, Heinrich Hertz, recognize the name Hertz? Well, he verified Maxwell's math and was able to experimentally produce electromagnetic radiation in the form of radio waves, a very low-energy form of light. In doing so, he observed an interesting effect known as the photoelectric effect. Here's an example of this effect. If we take an easy-to-oxidize metal, one that loves to give up electrons, and then shine high-energy light on the surface, we discover that electrons may start flying off the surface. This effect was used to build very sensitive instruments to measure light intensities. These devices were called photomultiplier tubes, or PMTs. Now, what was most startling about this discovery is what it implied. Light collides with the atoms in the metal, causing the electron to fly off the metal. The collision results seemed inconsistent with the notion of light behaving like a wave, something that would slosh over the surface of the metal. Einstein, in 1905, was able to formulate a mathematical description of the effect and reasoned that light, in this experiment, was behaving like a particle when it collided with the surface, not a wave. He was also able to calculate the energy of this particle of light utilizing a new constant of nature named after its discoverer, Max Planck, who discovered it when looking at how light interacted with something called a black body, a very cool experiment that's worth looking up on the web. Now, Einstein proposed that the energy of the light particle can be calculated by multiplying Planck's constant times the frequency of the light, where Planck's constant is equal to 6.626 times 10 to the minus 34th joule seconds. Einstein would say that this particle of light had a specific bit of energy or quanta of energy. Later, the great American scientist and spectroscopist Gilbert N. Lewis, a name worth remembering, would begin calling these light particles photons. We know that the frequency of light is equal to the speed of light divided by the wavelength. So we can substitute this relationship into Einstein's new equation and produce an extended version of the equation relating the energy of the light and the wavelength of the light. E equals h times frequency equals hc divided by lambda, the wavelength. You can see that if we desire the energy to be in the SI units of joules, the wavelengths must be in the units of meters, the time in units of seconds, and Planck's constant must have the units of joule seconds to cancel everything correctly. Here we have an equation which was discovered looking at light as a particle, but now incorporates light's wave nature through its wavelength. A truly puzzling result. So is light a wave or a particle? Well, probably both and neither. It can behave like a wave or it can behave like a particle depending on the measurement. But the truth about light ultimately lies in the mathematical description rather than the earthly subjective terms or pictures we tend to use and rely on. So let's put the complete electromagnetic spectrum of light energy in front of us. First, we have the energy of a single photon of light displayed. The equivalent frequency of the light is directly or linearly dependent on the energy, looking at Einstein's new equation. So the higher the frequency, the greater the energy of the light. The equivalent wavelength of the light, looking at the energy equation, is inversely proportional to the energy. So the smaller the wavelength of light, the greater the energy. The physical descriptions of the different energy regions of light need to be in our memory banks because they're used all the time in science. So moving left to right on the low energy side of the spectrum is radio waves, then microwaves, followed by IR or infrared light. We have the well-known visible region in the middle, and on the high energy side of things we have UV, ultraviolet radiation, X-rays, and the highest energy light of all, gamma rays. There's a ton of information on this slide, so study this particular graph carefully. Now that we have a bit more insight into the nature of light, and more importantly, can calculate a light's energy, we can move on to understanding more about how light can be used to probe matter. Its historical significance in helping us get at the true nature of matter and helping us see the electronic structure that governs the reactivity of the atoms cannot be overstated. Okay, that's it for now. See you soon.